Right, so for number 3 we've got the mass spectrometer, germanium atoms, and the radii of curvature in the mass spectrometer equal to 21 centimeters, 21.6 centimeters, etc. Okay, so this would be different ions of the germanium atoms that hit the detector at these radii. Okay, now the largest radius, which one would that be? This one, is it? Yeah, corresponds to an atomic mass of 76 atomic mass units. What are the atomic masses of the other isotopes? Okay, so let's see. Let's quickly just see what actually happened here. I have to refer back to when we explained how a mass spectrometer works, but just let's quickly go over it. So we've got a chamber here. We've got some positive ions being shot into an area with an electric field and a magnetic field, and there's this, in the original design, this kind of half-moon chamber here with a detector, and the positive ions come out here, and they've got a certain mass m and a certain charge q, and they go into move in an arc like this, as we explained in class, and hit it at a distance of 2 times from the slit, a distance of 2 times the radius of this half circle that it's moving in. Okay, it's moving in a circle because here is a second magnetic field, B. Well, I use blue for magnetic, so let's use blue again, B. Right. Okay, and the relationship between these terms is as follows, and this is something we derived in class. That is that the mass is absolute value of the charge, B prime R over E. Okay. Strictly speaking, we can drop the absolute value signs here because it's positive ions. But in principle, if you can get negative ions out of here, I mean, the same principle will hold. Alright, okay. And they're all hit here. The one hits with a radius of 21 centimeters. Other one hits close by, also at 21.6 centimeters, and at 21.9, etc., etc., etc. Okay. So now let's start the problem. That is just the background. That is what's happened. That's the experimental setup. Okay, so 3. Now I want to use this formula. And I'm after the M, the masses of these other isotopes of germanium. So this M is what I'm after. Now what do I have, what do I don't have? Okay, well, B prime E, that's the value of these magnetic and electric field and magnetic fields. That will be the same for all of them. The radius, of course, is different. But we're also going to assume that the charge of each of those isotopes hitting at these various distances are also the same. So all our ions with the same charge. Now, at the end, we'll talk about why that makes sense. Well, that's a very reasonable assumption. Okay, but we have to state that. So assume that all ions, well, not all, there might be other ones, I don't know, so let's say the ions, these ones that we're told about, that the ions that, well, they're referred to as isotopes, but specifically they are, well, more than that, they're ions. Otherwise they won't be affected by this magnetic field, so that they can move in this arc. So they're isotopes, yes, but they're also ions, and that's why they're hitting the detector at those distances. Okay, so but we assume that those ions that hit the detector have the same charge Q. Again, we'll talk about why that makes sense towards the end. Okay, so let's start with our formula. This is what we know. This is how everything relates. B prime R over E. Now, what do I know? I know that the largest radii, this one, 22.8 centimeters, corresponds to 76 atomic mass units. So in this formula, I've got the M and the R value for one of them. So let's write that down. So the M over R value, which is equal to Q B B prime over E, that's what it's equal to, you know, if you divide up by R. This we know for one of them is 76 atomic mass units over 0.22. I suppose I could have left it as centimeters, but okay, let's write it as meters. This is what I know. Okay, if you don't know how to start, a good way to start is just to write down what you know. Okay, and this B, B prime, E, and Q will be the same for all of them. So for all of them, these four terms in this configuration, this we know. It's 76 atomic mass units over 0.228 meters. Right. Okay, but now it's actually quite simple. So now what I'm after, for another one of them, let's start with this 21 centimeters one, 21.0 centimeters one. Let's suppose I want the mass for it. So let's write it like this, mass of 21.0. This is equal to Q, B, B prime, R over E. Okay, so can we work out what this is? We've got R, right? That's 21 centimeters, 21.0 centimeters. But what is Q, B, B prime, and E? I don't know what it is. Do I? No, but wait, that is from here. When I'm told that the largest radii, 22.8 centimeters, correspond to 76U. So that tells me that this ratio is equal to this part in green here. This part, I know what this is. I know what that is. So it's substituted. This is equal to 76U over 0.228 meters. Okay, and that I got from here. Times the radius. What's the radius? It is 0.210 meters. Okay, and then what am I left with? Okay, so let's calculate this. So it is 76 times 0.21 divided by 0.228. Okay, good, like 70. Nice. So it's 70 U. 70 U. So I could have converted this to kilograms if I wanted to make it SI, but then for, I'd like the atomic mass, and the unit for atomic mass is atomic mass unit. So if I convert this to kilograms, got a kilogram value, then I would have had to convert it back to atomic mass unit. So I just left it as atomic mass units. So I wrote down the units just to keep track of everything, so I wouldn't get confused. Okay, so there we have it. That is the atomic mass of the isotope, more than that, the ion, that hits the detector at 21.0 centimeters. Okay, so that is its atomic mass. Okay, so I'm not going to go through all this for the other ones. So this I'll leave to you. So this is not how I would answer it in the test. But so this similarly is for you specifically. Go and check that for the mass of the atomic mass of the ion, and also isotope that hits at 21.6 centimeters, is 72 atomic mass units. Okay, 21.9 is 73 atomic mass units, and mass 22.2 is 74 atomic mass units. Good. Okay. Okay, so let's perhaps quickly go over it again. I know this is the formula I want to work with. This is the first thing I want to calculate. What is the atomic mass of the ion, the isotope that hits at 21 centimeters? So I just use the formula, and I'm looking at this and I'm staring at it and saying, what is this? I know what R is, but I don't know what the other terms are. So how do I proceed from here? Go back. Let's see what I know. I know this equation is satisfied for when M is 76 atomic mass units and R is 22.8 centimeters. Now when I write that down, when I actually write down, it's often necessary to write down what it is that you know, so then you see what's happening. And I notice, wait a minute, but then this ratio is precisely equal to this entire thing. Okay, so this entire thing, I don't know what Q is, I don't know what B and B prime is, I don't know what is, but all of them together, I know what that is. Good. Okay, so now to end with, I want to talk about why it was reasonable to assume that all these ions have the same charge. Well, you can easily see from here. Let's look at this formula quickly, and let's get radius by itself. What is the actual radius? So the radius is going to be, let's see, what is this? Mass times the electric field in the first chamber over QB prime. Okay. Now, let's suppose I consider radius for 3 different kinds of ions. I consider this is the first one when the charge is like that. But let's suppose that Q is equal to 1. It's just E plus E. Okay. So plus 1. So 1.6 times 10 to the minus 19. Let's suppose that is the charge. And now let's suppose there's a second ion, but it doesn't have the same charge. In fact, it's got twice that. Then this is a half ME over QB prime. In other words, this is a half R1. Similarly, let's say if R3 is a third type of ion, and its charge isn't just plus E, but it's 3 times that, so it is 3Q, then similarly it would be a third R1. So if you have 3 kind of atoms, one with a charge of plus 1, the elementary charge, and the other one twice that, another one 3 times that, then the second one's radius would be half of the first one's radius, where it hits, and the third one's radius would be a third of the first one's radius. And the distance between the second and the third one would also be significant. Not as big, but the distance between a half and a third isn't nothing. It's what's it is a sixth. The sixth about what's a sixth? Sixth. Yeah, that's 3 over 6 minus 2 over 6, so a sixth. So yeah, it's like 16%. There'd be a 16%, well, closer to 17% difference between these 2 radii. But look at these, the radii that we're given in this problem. One is 21 centimeter, 21.6, 21.9, 22.2, and 22.8. They're very close together, these radii. So it seems very reasonable to assume that they all have the same charge, and instead what causes them to hit at slightly different spots is because they have different, those isotopes and ions, but they both have got different masses, you know, more or less protons or neutrons. And that is why they're hitting at slightly different spots. They're all pretty close together. If you add or remove a couple of protons or neutrons, then that's not going to change a whole lot where they hit, similar to what we're given here. But if you make, well, I shouldn't say protons, not protons. Protons mess with the charge. If there's isotopes, then it'll be, if it's isotopes, then it should be different neutrons. So just messing with the mass. If you add or remove a couple of neutrons, then it'll still hit close together. But if you mess with the charge by adding or subtracting, or adding or removing electrons in some way, then that will have a very big impact on where exactly the ions hit the detector, as you can get an indication from here. Okay, so that is just to explain why this is a reasonable assumption. Okay.